All right, thank you for the invitation. This is based on upcoming work, which will actually be on the archive tonight with Sylvie Pufu and Ross Dempsey. All right, so let's get started by discussing the theory, which will be the main topic of today's discussion, which is n equals 4 super Yang mills. So as I'm sure everyone in the audience knows, this is a maximally supersymmetric gauge theory in 4 dimensions, which is defined by its gauge group G, for instance, SUN, which will be the main topic of today's talk, a coupling G mills, as well as theta angle. And this theory is conformal for any value of the complex coupling tau, which is defined by combining theta and G mills as such. So I would say this is probably one of the most well-studied toy models in high energy theory for a number of reasons. One reason is due to ABC of T. So it is kind of the paradigmatic example of the holographic principle, and that it is dual to type 2B string theory on ADS5 process 5 for the SUN case, with the gravity description for large N and large tau. Another motivation of why people study it is that it's just the simplest gauge theory. Simplest in the sense that it's the most symmetric, because it has maximal supersymmetry and it has conformal symmetry. And so this, if you want to study something like QCD in 4 dimensions, this can then be a reasonable toy model to study. So it's a very well-studied theory, and there are many different approaches people have used to study it. So one approach is to study it perturbatively either in N or in the coupling. So if you're doing perturbatively in the coupling, that's just weak coupling. And then you could study n equals 4 the way you would study any gauge theory in 4D using Feynman diagrams. So that would correspond to small lambda, and you can do this for any value of n. Another approach, which is perturbative in n, but finite in lambda, is integrability, which usually is applied in the planar limit as n goes to infinity. And so it's very difficult to study most quantities beyond the planar limit using integrability. And so the limitations of these two perturbative approaches is that you cannot probe the quantum gravity regime, which is a regime where n is very large but not finite. And so if you're using integrability, you can only probe the classical string, whereas if you want to probe the quantum string, you would have to go beyond the planar limit. So this talk, instead of these perturbative methods, will combine the two known non-perturbative methods, which are supersymmetric localization and the numerical conformal bootstrap, which I will now briefly review. So supersymmetric localization for n equals 4 super Yang mills, it uses the Lagrangian of the theory to compute protected non-local observables exactly for any value of n and tau, as shown originally by Chester. So for instance, you can use localization to compute half BPS-Wilson loops for any value of n as well as any value of lambda. But for this quantity, there's actually no dependence on theta. There's no instanton contributions. So it's a simpler quantity than it could have been. Our focus is another non-local quantity called the sphere of free energy, f of n, which can be computed from any value of n and tau, where n is the hypermultiplet mass for which you can deform the n equals 4 theory in order to get an n equals 2 theory, called the n equals 2 star theory. So this was also computed for any value of n and tau in the original localization paper by Pestun. And what's interesting about this localization calculation is that when m is not 0, there is theta dependence via instantons, which are captured by something called the Nekrasov partition function. So the localization quantity is a bit more non-trivial than that which is used to compute half BPS. A limitation, though, of supersymmetric localization is that you cannot compute unprotected observables. Another limitation is that you cannot directly compute local CFT data. So for instance, you cannot directly use localization to compute scaling dimensions or OPE coefficients. So you're kind of limited to these protected non-local observables like sphere free energies and Wilson loops. So the other non-perturbative method that people have used to study n equals 4 super Yang mills is the numerical bootstrap. So this was initiated in a paper by Rosselli et al. A number of years ago. And you can use this method to compute non-perturbative bounds on CFT data that appears in the stress tensor 4-point function. And you can do this, in fact, for any n equals 4 conformal field theory in terms of the central charge C, which kind of describes the number of degrees of freedom in the theory. So for instance, they used the bootstrap to compute upper bounds on the lowest dimension unprotected scalar operator as a function of C, where, for instance, for the SUN theory, C is n squared minus 1 over 4. So here I'm quoting these plots from their paper from 6 or 7 years ago. And so as you see, the x-axis is related to C, which is proportional to n squared. And on the right-hand plot, you see they are focusing on the very large C regime and plotting it in terms of 1 over C. And one of the successes of this bootstrap study is that they were able to compare these upper bounds they were getting on the scaling dimension to independent calculations at leading order and large N as computed from supergravity. And they found some evidence that in the infinite precision limit of the numerical bootstrap, it seems like these bounds would maybe roughly saturate this supergravity correction, which is shown in red here. The limitation of this bootstrap study, though, is that they did not know how to impose the value of tau. So they could only impose the value of C, but not tau. And the reason is that there is no local CFT data which is known exactly in terms of tau. So of course, all the scaling dimensions of B coefficients generically depend on tau, but in some very complicated way. And so, but because you want to do a non-perturbative study, they didn't know something exactly in terms of tau, which they could input into the bootstrap and thereby study it as a function of tau. So that was a limitation of the previous study. And so in some sense, you could say numerical bootstrap is kind of complementary to localization, where numerical bootstrap allows you to study a very wide variety of things, all kinds of scaling dimensions and OB coefficients, but you can't put in tau, whereas localization knows how to put in the value of tau, but it's limited to way fewer quantities, only protected stuff and only non-local stuff. So in today's talk, I'm going to show how to combine these two non-perturbative methods to kind of get the best of both worlds. So in particular, over the last few years, I, along with these collaborators, have derived two exact relations between the mass deformed free energy and certain integrals of the stress tensor 4-point function. Where the intuition behind why we can derive these things is because mass couples to the stress tensor multiplet operators. And so thus taking derivatives of mass gives you integrated correlators of stress tensor operators. So previously, we applied these integrated constraints to the analytic bootstrap of the large N correlator to compute the lowest few protected coefficients in the higher derivative expansion of string theory around supergravity at ADS5 process line. So basically, we just take this 4-point function in the conformal field theory, we expand it at large N based on general grounds that fixes the kinds of functions that can appear. At each order in 1 over N, there's a very limited set of functions that can appear. There's so few of them that we're able to just fix them using these two integrated constraints. And so in particular, we were able to fix the two non-trivial corrections in 1 over N. One of them in the bulk corresponds to an R to the 4 correction, where R is the Einstein is a Riemann tensor. We were also able to fix the D to the 4 R to the 4 correction at large N for finite tau. And as a nice consistency check, we could then take the flat space limit and match this holographic correlator to the type 2B S matrix, and we got the same answer, as was previously computed by Michael Green et al. In papers, I guess, going back 10, 15 years ago. So this was a nice check because it was like the first non-perturbative encoupling check of ADS-CFT. But this was at large N and finite tau. In today's talk, we're going to combine the numerical bootstrap with supersymmetric localization now to compute quantities in the stress tensor correlator non-perturbatively in both N and tau. So there's no longer any expansion. It's just completely non-perturbative. And so I should note that the spirit of this study is similar to a previous study I did with these collaborators for the 3D ABGM theory, in which case we were also able to compute non-perturbative bounds, in fact, very precise islands for any value of N, and when the Chern-Simons level is 1 or 2, which is the case we have maximal supersymmetry. So the main novelty of the N equals 4 case versus this previous ABGM case is that in the ABGM case, we were able to do this without requiring integrated constraints. Because in that case, we had certain quantities known from localization that were just local CFT data. So what makes the 4D case much more challenging, but also richer, is that in order to impose this value of tau, we're going to have to use integrated constraints and combine that with the numerical bootstrap, which requires developing new methods. Okay, so let me give an outline of what today's talk will cover. So first, we're going to review the stress tensor 4-point function and previous weak coupling results for CFT data that appears there. Then we're going to review these two integrated constraints I just discussed and show how to compute the localization input in terms of a certain matrix model integral. Then we're going to show how to combine these integrated constraints with the usual crossing equations that one studies with the numerical bootstrap. And I will note that this will include lessons that work for general spacetime d greater than or equal to 2. So not just d equals 4, as this talk focuses on. Then I'm going to use these two combined things to compute bounds for the lowest dimension scalar operator called the Konishi for any value of N and tau in principle, although in practice, we're going to focus on N equals 2 and 3. Although our method in principle works for any value of N, and for any gauge. in particular. And then as a very nice check of our method, we're going to show that these weak coupling estimates to very high loop order match our non-perturbative results to pretty good precision, which shows that what we're doing is right. Okay, so here's the outline. So before I jump in, any questions from these first introductory slides? Great. Okay, so let's just jump right in. So let me review some basics about n equals 4 superangles. So firstly, any n equals 4 CFT in general has an SU4R symmetry, and they are all conformal manifolds with one complex parameter tau. The reason why this has to be the case is because the complex marginal operator appears in the stress tensor multiplet. So you're forced to have this conformal manifold. In particular, you can define abstractly any n equals 4 conformal field theory by the value of the central charge C as well as the complex tau. Now, I'm talking about defining it in the sense of the local data. Of course, if you want to discuss something like Wilson loops and more non-local stuff, you probably have to give discrete theta angles and other stuff. But at least for the purpose of this talk, it is sufficient to know just the central charge C and the value of the complex tau. Now focusing specifically on an n equals 4 superang mills. So this is a specific n equals 4 CFT. It's gauge theory, where the matter transforms in the adjoint of the gauge group G, which must be a compact classical Lie group. And for this talk, we're going to focus on G equals SUN. This is just the simplest and most famous case. Another aspect of the SUN n equals 4 superang mills theory is that this conformal manifold has a duality group, which is SL2Z. So that means in particular, you expect quantities to be modular invariant. Two special points on this conformal manifold are the values when tau equals I, you have a self-dual point with enhanced Z2 symmetry, and when tau equals e to the I pi over 3, you have enhanced Z3 symmetry. And so these self-dual points will kind of show up as special points in the rest of it. Okay, so now let's focus on the specific quantity we're going to study in n equals 4 superang mills, which is the stress tensor 4-point function. So for simplicity, we can consider the 4-point function of the superconformal primary, which is a scalar with dimension 2, which transforms into the 20 prime of the SU4R symmetry. So as one typically does in conformal field theory, you factor out the position dependence in order to define a quantity, which is a function of these two conformal cross ratios, U and V. So then you can also impose the superconformal symmetry by solving the superconformal Warren entities as shown by Dolan and Osborne, and a formal solution is given as follows. So there's two terms. There's one term which I call G short, which is completely fixed by the free theory. So in particular, it has no tau dependence, although it does depend on C. Then you have this factor theta, which is just fixed by symmetry. And then all the non-trivial information in the 4-point function is packaged into this T of U and V. So T of U and V, you can just think of as the 4-point function, and that's the thing we're studying. Everything else is basically just fixed by symmetry. So now we can expand this T of U and V in 4D conformal blocks, as usual by taking the OPE twice in the 4-point function. And here's the block expansion. So we have these two short terms, and so these take into account all the short multiplets. The short multiplets do not depend on tau, and they are linear in 1 over C. And that's why we can write them as F0 short plus 1 over C F1 short. So all the non-trivial stuff is in the first term, which is the sum over all the unprotected multiples that appear in this 4-point function. So these are all singlet long operators, which can have even spin in this specific OPE, and the scaling dimension just obeys this unitarity bound. So it has to be bigger than spin plus 2. And so the goal of the rest of this talk is to compute these scaling dimensions delta as well as these OP coefficients squared that appear in this 4-point function. Okay, so now let's review some perturbative results about the CFT data. So we can start with the free theory when the Tuft coupling is 0. In that case, you have long multiplets for each even twist. And then going beyond the free theory, people have computed the stress tensor 4-point function to 4 loops in a small Tuft coupling expansion for any value of n. So the most recent result at 4 loops was given by Flory and Pereira, but of course there are many other authors who computed previous loops going back many decades. And I should note as an interesting technical fact, the first non-planar correction actually occurs at 4 loops. So up to 3 loops, all your answers, you won't even see n, everything is just in terms of lambda, and you only actually see n explicitly appearing outside of lambda at 4 loops. This is because this is a protected quantity. So you can extract CFT data from this 4-point function computed at 4 loops. So in particular, you could extract the scaling dimension of the Konishi operator. And so here I quote this result, originally computed by Velijanin. It's a very nice compact result. And as you see, the first non-planar correction occurs at 4 loops. So the lambda to the 4 term. You can similarly extract scaling dimensions at OP coefficients of, in fact, all of the twist 2 operators for any value of spin. So I'm just showing you the spin 0, but the results are also known for any value of spin. If you go beyond the leading twist, things become a bit more complicated because now you have degenerate operators. But I'll talk about that in a moment. First, just to briefly note, there is another perturbative method, integrability. So this is perturbative in N, and people have used integrability at a leading order in large N in the planar limit to compute the scaling dimensions of any single trace operators, such as the Konishi operator, for any value of the coupling lambda, using something called the quantum spectral curve in these very beautiful papers, starting with these authors. Okay, so now let's review the list of relevant operators. So operators whose scaling dimension is 4 or less. So one of them is the Konishi. A question?
What loop order is this now known? I thought it was like 10 loops or 12 loops.
Well, okay, so if you want to include non-planar correction, it's only known to 4 loops. I mean, if you only care about planar, then it's principle is known to any order, because like integrability is finite lambda.
To work it out takes a lot of work. So people went to.
Yeah. So I don't exactly know the precise planar order people have went to.
I think it's like the 12 or 14 is summary people usually find.
Yeah.
And then, of course, for like numerical data, you have some interpolating.
But numerically, in principle, you have it for any finite lambda, and they can go to super high precision. So, anyways, okay. So let's discuss all the relevant operators. We have the Konishi, which we were just discussing, and then the next potential relevant operator is the one which, in the free theory, have dimension 4. So there are 4 such scalar operators, long multiplet operators, which in the free theory all have dimension 4. So we call these delta prime, and they are a mix of both single and double trace operators. So the unmixing at one loop was computed in this paper, and it's given by the solutions of this quartic equation. So you solve for omega, then you plug it into that formula to get the one loop correction. And you can see that in general, there are 4 real solutions. Specifically for n equals 2, there's just 2 real solutions, because for the SU2 theory, there's actually only 2 operators, because you just can't construct more. But then for any value of n, there's always just one negative solution. So that means only one of these operators, at least at weak coupling, is relevant, and the other ones are all irrelevant. One can also consider a different limit. So there's the limit of large n and finite tau. In this case, 3 of these operators drop from the spectrum because they involve single traces. The Konishi also drops from the spectrum because it's single trace. And then only one relevant operator remains, which is the double trace. And so we see that at weak coupling, there are 2 relevant operators. And at this large n very strong coupling regime, there's 1 relevant operator. And so it seems reasonable to conjecture that for any value of n and tau, there are probably just 2 relevant operators based on these various limits, what we have looked at. Okay, so this is the list of relevant operators. Okay, so now let's move on and discuss the integrated constraints, which is how we're going to input supersymmetric localization into our story. So we can deform n equals 4 super Mills by hypermultiplet mass m to get the n equals 2 star theory with the sphere free energy f of m and tau. So it depends on both mass and tau. Now, because mass and tau couple to operators in the stress tensor multiplet, so for instance, tau couples to the Lagrangian, whereas mass couples to various scalar operators, this means that derivatives of f of m and tau in terms of mass and tau give integrated stress tensor correlators after setting mass equal to 0. So this was shown in these previous papers, and these constraints take the following form. So you see that on the left-hand side, we're taking various derivatives of mass and tau. In one case, we take 2 derivatives of mass and 2 derivatives of tau. The other case, we take 4 derivatives of mass. And these relate to breaking down 4 stress tensor operators and then taking an integral. So they give integrated 4-point function. So the precise form of these integrals I2 and I4 I won't show, but they're given in our paper, and they're just certain integrals over S4. And then recall that the 4-point function is packaged into this quantity T of u and v, where for this specific formula, you also have to subtract off this connected or disconnected. And remember that this T of u and v is expanded in terms of the blocks, which involves the data we're trying to fix, which is the scaling dimensions and OP coefficients of the long multiples. Okay, so these are the 2 integrated constraints. But now what we want to do is we want to compute the left-hand side, these derivatives of f of m and tau, using localization. So let's see how we can compute this then. So as Chester showed in his original paper, I believe written at the IS, you can compute the f of m and tau using localization in terms of a rank G dimensional matrix model integral for general gauge group G. So if we focus on SUN, then we have very explicitly, in terms of these eigenvalues A, this n-1 dimensional matrix model integral. because it's rank n-1. So here in this matrix model integral, you have these h of z's, which are certain in Barnes G functions. And then you have the theta dependence, which shows up in the instanton contributions, which I've written as z inst magnitude squared. So if we were to ignore these instanton terms, then you can actually just compute this quantity using orthogonal polynomials exactly in terms of n and g nodes. And so this is something I first showed in my single author paper, and then we generalized it to this other integrated constraint in a paper with Sylvia. And so life would be very simple if there was no instantons, because we would just have the exact answer. You wouldn't have to do like a bunch of integrals. Unfortunately, though, we do have instantons, and so we have to take them into account. So how do we take these instantons into account? So this z inst, this is called the Nekrasov partition function, and you can formally expand it in terms of the instanton number k as such. And so you see each of these zk's is multiplying e to the 2 pi I k tau. And these zk's are actually known precisely, as shown by Nekrasov's original paper, and they are meromorphic functions, which are related to Young tableau with k boxes. So we can use these the explicit form of these functions to compute the mass and tau derivatives of the free energy. So we originally did that in the large n limit for finite tau in this previous paper with Michael Green et al. And we found that the answer was written in terms of various modular functions, as you would expect. So in particular, in one case, it was Eisenstein functions, in another case, it was more general modular functions. Not only can you compute it at large n, but in fact, for one of the localization inputs, Michael Green and his two collaborators were able to compute it at finite n in tau. So the answer was just known completely, although it was written in terms of an infinite cell. Unfortunately, they do not have such a compact expression for the other localization input, which involves 4 derivatives of mass. And so as a result, instead of trying to use these finite n formula, which I believe will be available soon, we've taken the more pedestrian approach of just brute force doing this matrix model integral, using the explicit formula for this zk inst. So that's what we did for this paper, and we just had to compute n-1 integrals. And so this is practical as long as n isn't too big. So in practice, we just expand the z inst up to a certain k. This expansion is extremely convergent because as long as you look in the fundamental domain, all of these terms are damped by e to the 2 pi I k tau. And so they're getting kind of exponentially smaller. So in practice, one only has to go up to even like k equals 1 or 2 to already get like 10 digits of precision, which is more than enough for our numerical purposes. And so then you could just do these integrals, which we did for SU2 and SU3, and you get the following result. So I will show you a sample. So this is for one of the localization inputs, the one that involves 2 derivatives of mass, 2 derivatives of tau. This is for the SU2 case. And so you can plot this localization input. The plot on the left is going from the free theory until the tau equals I, which is the Z2 self-dual point. It just takes the following form. It's this curve. The right-hand plot is showing going from tau equals I to tau equals e to the I pi over 3, which is the Z3 self-dual point. So this is just giving you a flavor of how this input changes. So you can see that on the left-hand plot, it changes rather noticeably from 0 to a quarter, whereas on the right-hand plot, the change is very small. So it's going just from like 0.2704 to 0.2718, but it is changing. Another thing you should note about these plots is that at these self-dual points, the slope is 0, which is what you expect because on general grounds, you expect that self-dual points on conformal manifolds should be critical points. Okay, so this is the localization input, and this thing can be in principle computed to any number of digits, just by doing your numerical integrals bigger, waiting longer, using a cluster, etc. Okay, so those two plots were showing specific slices of the fundamental domain. Here is a plot which shows the full fundamental domain. Because remember, we have a full complex parameter tau. And so the main fundamental domain we care about is this kind of middle region, as demarcated by these white lines. For completeness, we show the neighboring fundamental domains. And it's a little bit hard to see from this color plot because it doesn't vary that much in terms of the imaginary part of tau. But if you were to look very closely and if you just check the precise numbers, you would learn that the maximal value is at the Z3 self-dual point. Although admittedly, it's a little bit hard to see just from the variation of this color. So like the deepest red is right at that corner. Okay, so any questions about the localization input before I move on? Great. Okay, so that concludes the discussion of the localization input. Now let's discuss how to actually impose these integrated constraints on the stress tensor 4-point function. So we have the block expansion of the stress tensor 4-point function, And a technical difficulty is that this block expansion only converges in certain subregions of the full Euclidean space, R2. So that means you can't just naively apply these integrated constraints over the full sphere S4, because naively would diverge. And so the way you avoid this technical difficulty is that, first of all, let's consider these variables z and z bar, which we define in terms of the conformal cross ratios u and v. And then let's divide the full Euclidean space into fundamental domains under crossing symmetry. So every 4-point function has crossing symmetry because you could just permute the operators, and in Euclidean space, the 4-point function remains the same. And so because you have 4 operators, that means you have an S3 crossing symmetry. And you only need to look at one fundamental domain under that crossing symmetry because all the other fundamental domains are just identical and they can be related by crossing. So this plot shows you in terms of these variables z and z bar, the various pairs of fundamental domains. So there's 6 fundamental domains under S3. D1 and D2 and D3 are pairs of fundamental domains. The dotted lines show the individual fundamental domains. And if we're doing the block expansion in the S channel for simplicity, then it converges within the domain D1. If we wanted to expand it in the T or U channel, it would just converge in some of the other domains, D2 or D3. So in practice, we can just restrict the integration to D1 and then multiply the answer by 3. And that will give you a convergent answer, which would be equivalent to just doing the full integration. And so that's how we avoid this technical difficulty of our integrals converging to the block. Okay, so a few more details about applying integrated constraints to block expansion. So recall that our 4-point function was expanded in terms of short multiplets and long multiplets. And the short multiplets are somewhat trivial in that they don't depend on tau, they only depend on c, and you can in fact just resum them into these exactly known functions of z and z bar, f0 short and f1 short. So because these are just exact functions and they don't depend on tau, we can just compute the integrated constraints on them once and for all. And so we can just do this integral, it's some integral, you do it numerically, and you can do it to as much precision as you want. The long multiplets are much more complicated. So the long multiplets are captured by these conformal blocks, for every even spin L, and for in principle, any delta bigger than L plus 2. So if you want to compute the integrated constraints acting on these blocks, in principle, you could use the exactly known expressions for 4D blocks, which are worked by Dolan and Osborne, and then just for every value of delta and spin, you would have to do a 2-dimensional integral. Something which is a bit more convenient is that we use another way of expressing conformal blocks. So you can define these radial coordinates, r and eta, and then you can expand conformal blocks, in fact, in any space-time dimension D, in a small r expansion. And so the advantage of this expansion is that now you could do the integral over r analytically, because it's just some polynomial in r, as long as you cut off at some r max. And then there's only one numerical integral you have to do, which will be the eta integral. And so this makes your life a little bit easier if you're going to be doing integrals from any values of delta and theta. A couple of details about this block expansion is that the coefficients at each order in R, they consist of meromorphic functions in the scaling dimension, which are what these B's are, as well as Gegenbauer polynomials, which captures the dependence on eta. And so these will be a little bit important for some of the technical details going forward. Another nice aspect of using this alternative version of the 4D conformal block, this expansion in R, is that this naturally generalizes to any space-time dimension. So in this talk, I'm going to be talking about how to combine bootstrap with localization in 4D. But one of the exciting things about this program is that we can apply it in many other dimensions. And so, as I'm trying to explain, this method will just directly apply to any other dimension, because you could just use the general conformal block expansion in any dimension. There's nothing special about 4D from this perspective. Okay. So now let's talk about some technical details of the integrals of these conformal blocks, which will be important for the implementation. So previously, I showed you Euclidean space as written in terms of z and z bar, and I described how there's 3 fundamental domains under the crossing symmetry. Now let's look at Euclidean space in terms of the R and eta variables. So again, we have the regions D1, D2, and D3. And notice that the maximum in terms of R of the region D1 occurs when eta is 0 and R is 2 minus root 3. And so this means if you're looking at the integrated constraint acting on a conformal block, and if you're looking at very large values of delta, and if you want to have an estimate of how this integrated constraint grows with delta, it's just going to go like the maximal value of R within that regime. And so recall that the blocks in this small R expansion, they had this factor of 4R to the delta, and then just a bunch of polynomials in R. So that means at very large delta, they asymptote to 4 times the maximum value of R to the delta, which is 2 minus root 3. And so that's why we see that the integrated constraints are growing exponentially, like 4 times 2 minus root 3 to the delta. And then they're also oscillating in spin because Gegenbauer polynomials when eta equals 0 oscillate in spin. And so just the two facts to remember from this slide is that they have this certain exponential growth and they're oscillating in spin. And that's what these integrated constraints look like when acting on blocks in the asymptotic regime of delta. Okay, so that concludes how you act with the integrated constraint on conformal blocks. So just to briefly recap, we've discussed how you have a localization input, which is related to a certain integral of the 4-point function. And we've also showed you how these integrals of the 4-point function are applied to the block expansion. So that's kind of discussed the supersymmetric localization aspect of our constraints. I have not yet discussed the bootstrap aspect of our constraints, which is what I'm about to tell you guys next. Okay, so now let's review the bootstrap for the stress tensor 4-point function as originally described by Rastelli et al. So as usual in the bootstrap, you apply crossing under the first and third operator to derive these crossing equations, which is an infinite set of crossing equations because you have one equation for each value of the conformal cross ratio, u and v. So the crossing equations take the following form. You have the first term, which corresponds to the long multiplet blocks. And then you have these other two terms, which correspond to the short stuff, which recall doesn't depend on tau, so it's a bit more true. So now, as is typical in the bootstrap, let's consider some infinite dimensional vector space, which is functions of u and v. And then you can think of the cross-view equations as an infinite sum of vectors labeled by the scaling dimension and spin with positive coefficients given by this OP coefficient squared. And the cross-view equations is telling you that this infinite sum must equal a vector of short multiplets. And so that's kind of an abstract way of viewing the cross-view equations in this kind of infinite dimensional abstract vector space. So now on this vector space, we can consider a functional alpha, and we can use this functional alpha to bound the scaling dimensions and OP coefficients in terms of C, because C shows up explicitly multiplying this F1 short. And so that's how we're inputting C into the bootstrap. Another way of saying it is that C is related to local CFT data, and that's why intuitively we knew how to input C into the bootstrap. Okay, so let's briefly review these bootstrap algorithms. So for the bootstrap experts, this will be a review, and hopefully this will give some taste of how the bootstrap works for those who are less familiar. So let's first discuss how you get upper bounds on scaling dimensions, for instance, for the spin 0 sector. So we start by normalizing our functional alpha, such that when alpha acts on the short multiplet contributions, it equals 1. Then we search for functionals alpha acting on the long multiplet crossed blocks as parameterized by delta and spin, such that for all delta spin, for any spin greater than 0, such that delta spin is greater than or equal to spin plus 2, and specifically for spin equals 0, that the delta 0 must be greater than some delta star. And so we're searching for functionals for this regime of delta and spin. So if such a functional exists, then because the OP coefficient squared is positive, you can thus show that this sum over all delta and spin of OP coefficient squared times alpha acting on these long multiplet cross blocks is strictly positive. But this would contradict alpha acting on the 4-point function. And so this shows you that some assumption you made is false. In particular, this means that this bound delta 0 is greater than or equal to delta 0 star must be false. And so this gives you a disallowed point in the plane of C and delta 0 star. And so by running this algorithm for many different values of delta star, you thus get upper bounds on the lowest scalar operator as a function of C. So this is an upper bound. So I should comment that for a general conformal field theory, you could also compute a lower bound and thereby get an island, as people famously got for the Ising model, by putting a gap above this lowest dimension scalar operator and then just inserting an operator below that. But since Superyang-Mills is a conformal manifold, if you haven't put in the value of tau, which we have not yet, then you would never, your lower bound would just be trivial, because your lower bound would just be the free theory. And so there would be no point of even putting in a gap because you wouldn't really get anything from it. Okay, so this is the scaling dimension algorithm. Any questions about this algorithm? Okay, good. So there's a similar algorithm on OP coefficient squared. Again, I'll show it to you for spin 0. So now you normalize the functional such that it acts on the crossed block for some specific operator with some delta star and L.
Can you elaborate what you mean by algorithm?
Sorry?
Could you please elaborate what you mean by algorithm?
Algorithm is a set of steps which I'm using in order to compute bounds on CFT data. And I will give more details in the coming slides about how to make this algorithm practical so you can actually implement it on a computer.
And are the steps random?
No.
Because the definition of an algorithm is there's a randomness in it, otherwise you have bias.
Well, I've made my own definition then.
Okay.
Okay, great. Now I'll show this algorithm for the OP coefficient squared. So now you normalize the functional such that it acts on a specific operator for some specific delta star and spin star. And then you require that alpha acting on these cross blocks for all the other delta and spin, again, is positive. This is the same step as in the scaling dimension algorithm. And now you maximize alpha acting on the short contributions. And so this then gives you an upper bound due to the crossing equations, which says that this OP coefficient for this specific operator is less than or equal to negative times this functional. So just as in the scaling dimension algorithm, in principle, you could also get a lower bound by putting a gap above this operator and then inserting this operator. But again, because supernomial Mills is a conformal manifold, if you haven't put in the value of tau, there's no point of doing that because you wouldn't get anything. Okay, so here I just reviewed the two algorithms that were used in Rosselli et al.'s original work in order to bootstrap n equals 4 superrings. But so far, I've just described abstract algorithms. I haven't given you details about how you actually practically implement this. So the next couple slides are going to be a bit technical. And so they're more intended, I guess, for the bootstrap experts in the audience who want to see how we modified things. So if you're not following everything in the next couple slides, don't worry. We will give the results right afterwards, and that's the more physically interesting part. Okay, so to practically implement these algorithms, we need to truncate three kinds of infinities. So the first infinity is the range of spin that occurs in the block expansion, because in principle, it goes over all even spins. So it's very easy to deal with this. We just truncate to some cutoff L max, and this works in practice because the block expansion converges very quickly for large scaling dimension, which is related to spin. This was shown by Slava et al. In a number of papers. The second infinity is the fact that our vector space is infinite dimensional. It's all these functions of u and v. The way this is conventionally dealt with is that we just truncate to some finite dimensional subspace. So in particular, instead of looking at any function of u and v, we look at derivatives of z and z bar with all derivatives up to some cutoff capital length around the crossing symmetric point. The third infinity is the fact that the possible set of operators also is this continuum of delta, where delta is going from the unitarity bound in principle up to infinity. So the way this is dealt with is a bit more subtle than the first two infinities. So recall that the conformal block in this R expansion scaled like 4 to the delta times some meromorphic function of delta. So in practice for our bootstrap algorithm, we expand the conformal block up to some R max. We take our z and z bar derivatives, evaluate them at z and z bar equals a half, and then we redefine the OP coefficient squared, which multiplies these blocks by some positive quantity, which is given by 4r to the delta times poles in delta, where r is evaluated at the crossing symmetric point. And so this allows you to evaluate the OP coefficient squared times the z and z bar derivatives of our cross block in terms of a polynomial in delta, where note that r at this crossing symmetric point is 3 minus 2 root. So the advantage of rewriting this quantity as a polynomial in delta is that within the bootstrap algorithm, you now have polynomial constraints. And so that means you can solve them using semi-definite programs such as STBB, which was developed by David and Walter Long. So that's the conventional bootstrap algorithm, which I'm sure people in the audience have heard many talks from in the past. So now let's see how we have to change this though if we want to add in integrated constraints. So now, instead of just having a functional which just acts on functions of u and v, we're going to add two more elements to this functional, which I call alpha 2 and alpha 4. And they're acting on this bigger vector space, which will also include an integrated constraint acting on the function of u and v. And there's two integrated constraints, so we have I2 and I4. And so all that means is that in all the bootstrap algorithms I just showed you, you're just going to add these two new elements of the functional acting on the respective integrated constraint. So for instance, when normalizing alpha to 1, which was the first step of the various bootstrap algorithms, the first line is what we had before. So the first line is just as usual, alpha acting on these cross blocks for the short multiplets. The second two lines is the new thing we have due to the integrated constraints. And so this is basically implementing these integrated constraints. So it's saying that like I2 acting on this short stuff has to equal the localization input. Similarly, I4 acting on the short stuff has to equal its respective localization input. And so this is how we're inputting tau into the bootstrap. because tau enters into these derivatives of the mass to form free energy. And so then again, instead of looking for a functional just acting on the cross blocks, now there's two new elements of the functional, alpha 2 and alpha 4, which are now going to be acting on integrals of these blocks. And so you just run the same algorithm, but with these slight modifications. And now if you can find such a functional, then because alpha acting on crossing integrated constraints would contradict this, this would imply that your assumptions were false. So that means the specific choice of C, tau, tau bar, as well as your delta star is a disallowed point. And so this is how you're able to get disallowed points now in this expanded domain, which includes tau and tau bar. And so this is a big improvement over Rosselli et al.'s previous algorithm, which was not sensitive to tau and tau bar. And notice that we have two integrated constraints, which is why we're able to fix both tau and tau bar. Okay. So just one more technical slide before we get to the results. So recall that the integrated constraints in the Crossy equations scale at large delta in a different way. So the Crossy equations, they scale like 4 times 3 minus 2 root 2 to the delta, because that's what R is at the crossing symmetric point, 3 minus 2 root 2. Whereas the integrated constraints, recall we discussed before, they have this different asymptotic scaling and they're oscillating in spin. And so this causes a few technical problems. So the first problem is that because the integrated constraints oscillate in spin and dominate at large delta, this means that you would just trivially find that alpha 2 and alpha 4 are fixed to 0. Because you're demanding that alpha acting on a bunch of stuff has to be positive. And because each term in your sum is oscillating, that means each term is then just fixed to 0. And so this kind of unfortunately would make your algorithm trivial. The second problem is that the integrated constraints scale exponentially bigger than the Crossy equations. And so in the traditional approach to the conformal bootstrap, you wanted to approximate your constraints by polynomials of delta. And you could do that even though there was this exponential factor by just factoring it out and like redefining your OB coefficient. But now that you have two different kinds of exponential scaling, you can't approximate both of them by polynomials. Because like if you factor out one exponential scaling, the other one is still going to be exponential. And so this just means that you can't effectively approximate both things by polynomials. Now, one thing you might try is you might say like, okay, what if I just expand the Crossy equations around some other point, not the crossing symmetric point, which would give some different exponential scale. You could do that, but then that would lead to oscillations in the Crossy equations. So that would put you back to problem 1. And so this is kind of the technical difficulty in combining integrated constraints with the numerical bootstrap. And this is why it took us a few years to get this working. I should note that there had been a previous study, which in 2 dimensions for a certain supersymmetric theory, where they had also combined the numerical bootstrap with integrated constraints. And so in their case, the way they solved the oscillation in spin is that they deformed the regime of integration into some larger region, so outside of just this one fundamental domain D1, such that the maximum for R is no longer data equals 0, so the Gegenbauer is no longer oscillated, so you didn't have oscillations anymore. The problem with that solution is that this made R max even bigger. And so that means the exponential scaling for the integrated constraints was even more different than the crossing equations. So the way they solved that is that they just kind of did a very brute force approach of just approximating an exponential by a polynomial. And so like miraculously, that seemed to actually work in their 2-dimensional case. But this kind of crude approximation did not work in our 4-dimensional case. I guess there's no reason why it had to work. So if anything, it was a mystery why it did work for them. So in the sense that it didn't work, I just mean that it made the alpha 2 and alpha 4 components of the functional just trivial. So it just made our constraints not sensitive to tau. So the way we got around this technical difficulty is that we went back to linear programming. So in fact, the original way that people had done the numerical bootstrap in the original papers by Slava et al. Is that instead of doing semi-definite programming, they just discretized delta. So you put a bunch of steps in delta, you went up to some finite delta max, you did that for every single spin, and then your bootstrap algorithms just are a bunch of linear constraints, and you could just solve them with linear programming. And as long as the discretization was sufficiently small and the value of delta max sufficiently big, this did not affect the numerical results. So we applied this approach to combine the integrated constraints with the crossing equations. And the way this avoided the previous 2 problems is that because you have a finite delta max, this ensures that the oscillating spin and the different exponential scaling do not matter as long as we use sufficient precision for a given value of delta max in our linear programming software. And so in particular, we used STBB because semi-definite programming is just a more general version of linear programming. And it's a very effective linear programming software. Particularly allows for arbitrary precision. Okay, So the last few slides were very technical, and I understand maybe not everybody was following. This was more for the Bootstrap experts. But now let's get to the meat of this talk, which is our results. So if people just like weren't following the last few slides, now is the time to pay attention. Okay, so here are our results for upper bounds on the lowest dimension scalar unprotected scaling dimension. So on the left-hand plot, we are going from the free theory point, where G nils is 0, up to the Z2 point, which is the value 1, and even a little bit beyond to the Z3 point. And then on the right-hand plot, we are zooming in and showing how you go on a certain slice, which goes along the arc of the fundamental domain from the Z2 point to the Z3 point. So all these bounds are right now for the SU2 theory. So I can tell you that we also did it for the SU3 theory, but for simplicity, I'm just going to show you SU2. And as a technical comment, we use this bootstrap parameter with derivatives up to lambda equals 39, which kind of shows how converged our numerics are. So the really beautiful part of this plot, which you should focus on, is that these colored lines show the weak coupling estimate for the Konishi operator and see that it is remarkably close to our upper bounds. Like, and by remarkable, I mean like in a way bigger regime than you would have even possibly hoped for. So like, you know, these are in principle asymptotic series. And so maybe you would have thought that like, even if our upper bound was really describing the physical theory, maybe you would have only found a match up to like 0.1 or something. But when we include the full for loop result, and in particular do a PAD-A approximate, then we get this remarkable match like all the way up to 0.5, which I think is very nice. And so I think this suggests that our upper bounds are very close to describing the physical theory. And furthermore, it's a very non-trivial check on these super complicated weak coupling computations, which recall go beyond the planar limit, at least at 4 loops. Another nice thing you can see from these plots is that the maximal value of the upper bound occurs at the Z3 point, which is something you can really see by looking at the right-hand plot. So like the difference in dependence on tau is a little bit weak when going from the Z2 to the Z3 point. You see the y-axis is, you know, several digits. Nonetheless, you can see there's a clear maximum at the Z3 self-dual point. Another interesting thing to notice is that we can compare the upper bounds we got from our algorithm, which combined integrated constraints with the bootstrap, to the upper bounds you would have gotten at the same level of bootstrap precision, so at lambda equals 39, but without including integrated constraints. And that's what's given by this horizontal dotted line. And you can see that it is strictly weaker than the upper bounds we got with integrated constraints. And so this shows that the previous bootstrap study from 6 or 7 years ago, none of those upper bounds were being saturated by any physical theory, because those bounds were just strictly weaker than the bounds we're getting now. Of course, it's not 100% that even our bounds are being saturated by the physical theory, but I would say that based on this evidence of weak coupling, I think there's good reason to believe that perhaps in the limit of infinite precision, or perhaps by including additional Crossing equations, we are very close to having a solution to the physical theory at the upper bound, which would be basically a numerical solution to n equals 4 subgradient. So I've shown you these bounds for the SU2 theory. We've also computed the bounds for the SU3 theory, which you can see in our paper tonight. They look very similar, except at the Z2 point, the value of the y-axis is a bit bigger. And so I guess this kind of shows a general trend that as n increases, I assume that value will get bigger and bigger. And eventually we plan on looking at every value of it. Got a question?
So do you see like when you increase the number of derivatives, it doesn't move much?
Okay, so that's a good question. So I think we have pretty good convergence because lambda equals 39 is like a pretty big value. So like, I mean, it's like a bigger value than it's used in most bootstrap studies. So I think we have pretty good convergence. Of course, you know, for the right-hand plot, you know, like the y-axis you see is like varying very little. And so like to get to enough precision that you could be 100% sure about that, maybe we want to go a little bit higher. But I think we already have enough precision, certainly, to see this qualitative dependence, to see the fact that the maximum is at Z3. So I don't think
it will just saturate, right? You don't want it to overshoot.
Yeah, exactly. So I think certainly the weak coupling regime, I think it's very changing. You know, as lambda would get even bigger, because this really is a very big value. You know, for the bootstrap experts, we're familiar with this capital lambda. Okay. Any other questions? Yeah, so these plots are really, I guess, the main results. So like maybe I can give you guys a few more seconds to kind of stare at them. You know, and so like, you know, for those who remember seeing the talk about the icing model from a few years ago, like the original paper where they found that kink, and the big result was that they got this kink to be close to the Monte Carlo value. So I would say that these plots are the version of that for n equals 4 super ignos. because now we similarly have upper bounds, and we're finding that some independent theoretical estimate is really very close to saturating those bounds. Except the difference, of course, is that in the Ising model, you just had one isolated C of t. Whereas for n equals 4 sigma Mills, you have a conformal manifold. So like this plot is almost like an infinite version of the Ising model plot, where every single point we're finding that the upper bound is very close to being saturated by the physical theory. Okay, so if there's no further questions, I'll move on to the next slide. So now this shows the upper bounds as a function of the full fundamental domain. So not just the slices which were discussed in the previous slide. And as you see, just like in the plots of the localization input, you find that it depends very weakly on theta, which is the imaginary part of tau. And so this shouldn't surprise you, because after all the dependence on tau is coming from the localization input. And so because the localization input itself depended very weakly on theta, so too our bounds depend weakly on theta. On the other hand, they do depend on theta. I mean, because like, as you saw from the previous slide, from this right-hand plot, that's showing the dependence on theta, and you see it's changing. The point is just that the change is rather small, and so you have to look very carefully in order to see it. Okay. Now we can go a step further. So far I've showed you upper bounds, but people who might be familiar with the Ising bootstrap recall that they got not just upper bounds, but they eventually got islands. And they got these islands by imposing a gap and inserting the number of relevant operators. So ideally, what we would like to do in our case is we expect there's 2 relevant operators. So we would like to put a gap to 4 and then insert both of those relevant operators. Now, so far, we do not have enough bootstrap accuracy to be able to really pin down the second lowest operator. So I think we have the lowest operator very accurately, as we saw from comparison to weak coupling. But the second lowest operator, the bootstrap doesn't know precisely where it is. So like, it's still in some kind of hazy window from a little bit above 4 to a little bit below 4. And so because we don't have enough accuracy for the second lowest operator, we cannot get rigorous islands. But just to convince you that we will eventually get islands, one can just impose these semi-arbitrary gaps. So these gaps are basically saying that you allow operators at this value and above, and then you insert one operator below. And so for instance, on the left-hand side, you could put this gap to 3 or 3.5. And what you see happens is that a lower bound develops, which starts going up to meet the upper bound as you increase this gap. And then the right-hand plot is just zooming in on the region very close to weak coupling. And so what this shows is that because the upper bound is barely moving, it's really the lower bound which is moving. This, I think, really gives good evidence that once we have enough bootstrap precision to really see the second lowest operator, we will really see that we will get islands at basically the value of the upper bound that we're currently getting. So we don't have rigorous islands yet, but this plot is convincing you that we're very close to doing it. So any questions about the
solid line which is the upper bound and which is the lower?
So the upper bound is just the highest black line. And you can see like these different shaded regions are showing, I guess, the allowed region, depending on the gap you've put in. And so like the deeper orange on the left-hand plot is with a gap of 3.5. The lighter color includes the deeper orange and the color below it. And so the upper bound is always the same. It's always the highest black line. Sorry, I guess we should be more clear about that. And the thing which is changing is the lower bound, which is these other black lines. But the upper bound is always remaining the same. So the lower bound is coming up to reach the upper bound as the gap is increased. I mean, because the intuition is that if you put a huge gap, you would just get everything this low, because that would just contradict the physical theory. So like the true gap in the weak coupling regime is what's predicted from these weak coupling estimates, something a little bit below 4. But I think we need more bootstrap accuracy to really kind of pinpoint the second lowest operator at that precise value. Any other questions? Okay. So here I'll also briefly show you some bounds and LP coefficients. So these are a little bit less accurate than the scaling dimensions, because the way we compute them is that we first input the value of the scaling dimension, assuming it saturates the upper bound, and then compute the upper bound and the OBE coefficient. So they're kind of qualitatively similar, except a little bit less accurate. And so you see the match to weak coupling is a little bit weaker, but I think that's just a matter of precision. So I think this is something which will improve in time. Okay, so let me conclude. So we've showed how to combine integrated constraints with the numerical conformal bootstrap in general. By in general, I mean, we showed that for any space-time dimension, this is how you could implement integrated constraints such that they would effectively be seen by the bootstrap. And so this is something which you could apply not just to 4 dimensions, but also to 3 dimensions, 5 dimensions, to any other dimension. In particular, for the case of n equals 4 sigma Mills, we applied these two localization constraints, which depend on supersymmetric localization, to bound CFT data in the stress tensor 4-point function for, in principle, any gauge group and value of tau. So the method works in principle for anything. In practice, so far, we've applied it to the SU2 and SU3 theory, and we used it to bound the lowest dimension scalar operator, which in the weak coupling regime is called the Konishi. And so we computed its scaling dimension OP coefficient for any value of tau. And we found, without a gap, that we got an upper bound, which seemed very close to being saturated in the weak coupling regime by these 4 loop results. So this was like a very remarkable saturation, I would say. And then once we started exploring putting a gap above this operator, which eventually would be justified, because eventually we put a gap to 4 and put 2 operators below, we start seeing that very small islands start forming for each value of n and tau. So you could say, like, comparing to the icing model, so far we have the kink, and we're kind of getting to the point where we'll also have the island. We're not at the island yet. Another nice thing we observed is the maximum of the CFT data occurs at the Z3 self-dual point. And so this is kind of a question people had, from the original Bootstrap study many years ago, like, what value of tau maximizes it? And so now we've got good evidence that it's the Z3 self-dual. So there are many, many future directions which we look forward to exploring. So firstly, one kind of annoying technical difficulty is that if you want to compute this localization input, you have to do all these integrals. So in particular for a gauge group G, you have to compute rank G integrals. And so for SUN, there was n-1 integrals you had to compute. And so it would be nice if we just had some closed form expression instead of having to do these integrals brute force. So one of the localization inputs, so there's 2 of them, one of them actually already has been computed for the SUN theory for any value of n and tau in this nice paper by Michael Green et al. And if you were to ignore instantons, in fact, it's known for both inputs from these papers. But it would be nice just to compute it for both inputs, because then we could very efficiently explore n equals 4 secret mills for any value of n, not just for SU2 and SU3. And it would also be nice to generalize that to more general gauge groups, so we could explore SON, USB2N, exceptional groups, etc. Although I believe for the exceptional groups, the instanton formulas are not completely known. But I think for the orthogonal and symplectic groups, they are known. It would also be nice to improve the bootstrap precision to see more of the spectrum of n equals 4 secret mills. So in particular, as a first step, we would like just to see the next relevant operator. So we have a very accurate estimate of the lowest operator, but the second lowest operator is not as accurate. And so we would like to get that second lowest operator to be more accurate. And I should note this is a general issue with the bootstrap. So like even with the icing model, like the higher the twist of the operator, the harder it is to get an accurate estimate. So in particular, if we could get the second lowest operator to be more accurate, then you could impose this gap to 4, insert these 2 operators below, and this would give you rigorous islands, just as was done in the icing model case. So 2 methods we're approaching in order to try to get to this point. So one thing is just to brute force increase the bootstrap precision by increasing the value of capital lambda, and it's conceivable that by doing that and with lots of computing power, maybe we could just get these islands. Something which is a bit more intelligent, though, is to look at a mixed correlator system. So far we've just looked at a correlation function of the stress tensor operator, but we could look at mixed correlators involving the second lowest half PPS single trace operator, which I call S prime. So this is an operator which has dimension 3. It corresponds to the second lowest KK mode from the bulk perspective. The crossing equations have already been worked out in these previous papers, including my recent paper, Fernando and Tobias. And so everything's kind of ready to go. Like people did the numerical bootstrap without integrated constraints. So all we need to do is upgrade that by adding in integrated constraints. And so there are kind of 2 advantages you get by looking at this mixed correlator system. So firstly, in the paper I had with my collaborators a few years ago, we showed that there are integrated constraints, not just for the stress tensor 4-point function, but in fact for an infinite family of 4-point functions. So any 4-point function that has 2 stress tensors and 2 other half PPS operators, there is an integrated constraint. And so that means in principle there's infinite of them. But in particular, for SS, S prime, S prime, there's just a 3rd integrated constraint, in addition to the 2 we discussed in this talk. So by doing this mixed correlator system, we will have a 3rd integrated constraint, which I expect will vastly improve the accuracy of our results, even more than we already have. Another nice thing is that just in general, when you do mixed correlators, there's all kinds of bootstrap tricks you can do which improve your precision. So like, for instance, like you can demand that an operator which shows up in multiple correlators is unique by scanning over its OP coefficient and similar such tricks, which in the case of the IC model really made their islands much smaller. And so that's something we plan on pursuing in the near future. We have kind of everything set up. So we have the localization input computed, we have the bootstrap computed, it's just a matter of kind of putting it all together. One nice thing is that if we could determine the spectrum, the low-lying spectrum of CFT data for general n, then as you would increase the value of n, you would see the emergence of the expected holographic gap at the large n and strong coupling regime. And so, like, for instance, say you were to look at all operators of dimension 10 and lower of spin 0, you would expect that for small n and weak coupling, there would be many, many operators, as you would expect from a generic gauge theory, whereas in the large n and strong coupling regime, there would be fewer operators. The spectrum would get sparser, because in the large and strong coupling regime, the theory is dual to gravity, and so we only expect to see double trace operators for sufficiently large. So this is a nice thing we look forward to seeing in the future once we can explore the full range of n. Another thing is that I want to emphasize the generality of this new method we're proposing. So this new approach of combining the Bootstrap supersymmetric localization, it's not just useful for n equals 4 super Mills. It applies to literally an infinite family of quantum field theories. So in particular, any supersymmetric quantum field theory for which you can apply localization, you can apply our method. So in particular, for any 3D n equals 2 theory, for any 4D n equals 2 theory, and for any 5D n equals 1 theory, as long as it has a Lagrangian, as long as it's a CFT, we can apply our method. And so we expect that the same way that we are very close to solving n equals 4 super Mills numerically, we expect the exact same methods we'll be able to use to solve all these other families of theories. So in particular, a couple of theories I'm particularly interested in exploring in the near future. One of them is 4D n equals 2 SQCD. So like n equals 4 super Mills, this is a conformal manifold with one complex dimension. So it's kind of the next simplest guy to look at. But because it has less supersymmetry, it's a much richer theory. In some sense, it's closer to physical QCD in the sense that the matter field no longer transform in the adjoint. And so there's just like a lot more you can explore in this theory. And the hope is that there are enough integrated constraints that you can fully fix this conformal manifold. And so I can already say that there are 4 integrated constraints and there's just one complex dimension. So I'm hoping that should be enough. Another theory we'd like to look into is 3D n equals 6 ABJM. So what's nice about this theory is that depending on its parameters, it's dual to either string theory, M theory, or higher spin gravity. And so this generalizes the max place supersymmetric case, which was only dual to M theory. So in the max place supersymmetric case, in a paper with these collaborators from a few years ago, we were able to compute very precise islands. So in some sense, you could say we numerically solved the max place supersymmetric case, and we were able to do this for any value of n, but we were only able to do it for the max place supersymmetric case. The reason we could not do this less supersymmetric case of 3D n equals 6 is because the theory is described by 3 parameters. So it's a UN cross UM gauge theory, which turns out is level K. So you need to input 3 parameters to fix that. And we only had 2 inputs before, which was the value of C, as well as a certain OP coefficient we could compute through localization. But now that we have this new method of integrated constraints, we have additional integrated constraints, which will be sufficient to fix these 3 parameters. And so that's another thing we look forward to exploring in the future. Okay, so I think that's it. Question?
Yeah, so do I understand correctly that the biggest stumbling block now is getting general and data in particular when there are instantons from the localization result?
I wouldn't say it's the biggest stumbling block. I think like the main thing we're focusing on is just getting more accuracy in the Bootstrap, because it's like, even for n equals 2 and n equals 3, we just want to be able to see the second lowest relevant operators so we can get islands. Because then we can really say we've like solved n equals 4 super Mills, at least in the sense that people said they solved the icing, which maybe was an exaggerated sense, but like at least there's a tradition of using these words. The reason why I don't think the value of n is as much a stumbling block is that, first of all, in principle, you could just brute force these integrals for larger values of n. Like we did SU2 and SU3. I, on my own, did SU4. We did not including it in the paper, and I'm sure I could even push it if I used some supercomputing cluster to SU5, SU6. You could use Monte Carlo methods to value these integrals. Like, I don't think that's such a stumbling block. The other thing I can say is that, just in the last few months, Michael Green et al. Already computed one of the inputs at finite n and tau, and I'm sure the other input could be computed at finite n and tau as well. I think it's just a matter of time. So like, I'm sure that result will be available very soon, and so I wouldn't see that as the biggest stumbling block.
When you were plotting just the perturbative QFT data,
Yeah.
did you just plug in some value of lambda, or you did some kind of resummation?
Okay, so yeah, I can go back to that slide. So like we did just the crude loop data, but then we also did Pade approximation using the for loop data. So here you can see there's 3 colored lines. So red is 3 loop, green is 4 loop, and then blue is 4 loop pad. This is the 2-2 pad. So this was inspired by your papers, right? You're a big fan of pad. And indeed, the pad worked wonderfully in this case. So you can see how like the blue line is even nicer than the red and green lines. So this is also an advertisement for pad, I would say.
And you also include, say, some incorporate instant on.
Well, I mean, this is the weak coupling regime, so like you're not sensitive to instantons. And people don't know how to, I mean, so like there is a regime which is large n and finite tau, in which case we have computed CFD data, so several orders in large n and finite tau. This was in the papers with Michael Green et al. And so in principle, I guess once we have numerical results for large n, we can maybe try to compare it to that.
People do this resurgence. Maybe this can help to more precisely.
Oh yeah, okay. So there were a number of papers by Rastelli and Ashok Sen and other people where they were giving kind of conjectures of how you could upgrade these weak coupling estimates to be like SL2Z invariant. But I mean, they were all very conjectural. You know, it's like none of them were kind of rigorous. And so, I mean, I encourage those authors to compare to our data, but for our purposes, we restricted ourselves just to the weak coupling. Question?
Well, I think in the paper of Rastelli et al, they were conjecturing that I think it was the dotted line there. Was the value at the maximum at I think it's the C3.
Yeah, so I think that conjecture is false.
Okay, yeah.
Although, okay, in defense of their conjecture, I mean, first of all, the gap is not huge between Z3 and that line. So like, you know, they weren't like really far off. And secondly, you know, this is the SU2 result. If you look at the SU3 result, you'll see that the gap between the no integrated constraints and the yes integrated constraints gets even smaller. And so my expectation is that as n gets bigger and bigger, the gap's gonna get smaller and smaller, such that for very large n, their conjecture will be correct. And after all, this isn't surprising because at super large n, you know, the plot in the very first slide of my talk was showing Rastelli's results, and they saw that like the very large n upper bounds were very close to being saturated by tree level supergravity. And so I think like it's expected that for sufficiently large n, some conjecture of their type would probably be okay. Although I should also comment that if any theory were to be saturating the bound without integrated constraints, it wouldn't be the SUN theory, it would be the SON theory. Because that in the large n regime has strictly bigger CFD data. So this is something I pointed out in my paper with Fernando from last month. Although of course, once you input in these integrated constraints, you know, that issue becomes moot because you're just fixing the theory.
Shai?
Yeah.
Hi. So in the Beam et al. Paper, they also had this golden cube where they plotted the lowest dimension scalar spin 2 and spin 4 regions. And so the conjecture there was that the theory at the corner is the extremal theory where these 3 dimensions are simultaneously extremized. Have you thought about looking at the higher spin ones? Because there's an interesting question of how much of the golden cube the theory actually occupies, which you could access if you had plots like this for all 3 spins.
Yeah. So it would be certainly very interesting to look at higher spins. We kind of briefly explored looking at spin 2. The bounds were a little bit weaker than spin 0. I think we need a bit more bootstrap accuracy to get a similarly accurate estimate for spin 2. I think we'll eventually get there, but we haven't done a proper exploration of higher spins yet. So far we've just done spin 0, but yeah, it would be very interesting to look at higher spins. I mean, in principle, once we can get islands, you could just look at, you know, solutions of the functional along the boundary of the island, and from that you could read off all the higher spin data. And so that's another thing we could explore.
Thanks.
More questions for Shai? All right, let's thank Shai for a great talk.